now we are going to start looking at problems at the next higher level of abstraction. So we started off by looking at sliding window protocol at the data link layer, then we looked at routing algorithms in the network layer and deadlock free packet switching algorithms. We are now going to move one level higher into the application layers, where we will slowly start looking at different kinds of distributed algorithms, which are going to be part of algorithms that you will implement in programs and distributed applications. So the first fundamental thing that we need to look at is how do we manage the synchronization between different processes, and how do we manage the notion of time. And not only time, the other important thing is causality, that in time, if something causes something, then the thing which is caused happens after the thing which triggered it, right. So in a distributed system, it is quite possible that some event in node A leads to some event B in another node, and then we should make sure that if we order the events on time, and the third person who is seeing both of these must be able to infer that this happened and that caused that happen, okay, that event A caused event B. That is what is called causal ordering. So the third person has to be able to order the events and sequence them in the order in which they were caused, right. The real time is not so important, causality is important, right. Now let us see that what kind of problems can there be if we are not able to manage time correctly. So let us say that I have a database in which we have two sites, let us say site 1 and I have site 2. Now there is an account S1 in site 1 and an account S2 in site 2, and these are accounts of some bank database, and we want to run a transaction which will transfer from account S1 to account S2, right. At the same time, there is another transaction. So this is the transaction T1, and at the same time there is another transaction T2 which wants to compute the total balance of the two branches. Right. Now to compute the total balance of the two branches, T2 will record the balance of one site and then record the balance of the other side and then add it up, right, and that transaction can happen concurrently with T1, right. Now suppose that it happens in this way, that to perform this transaction we do S1 minus 10,000, okay, and then sometime later we will do S2 plus 10,000. Now what happens is that the state of S1, okay, is recorded here, state of S2 is recorded here and then added up and produced. What is going to be wrong? The total balance will be short by 10,000, right. Now, also look at another situation. This is one possible problem. Consider another situation where the state of S1 is recorded before the deduction. So, we record the state of S1, then we do S1 minus 10,000, right, and then we do S2 plus 10,000, then we record S2, the balance of S2. This blue is one transaction, red is another transaction. The red one is the transaction T1, the blue one is the transaction T2. What is going to happen here? The balance will be shown as 10,000 extra, right. Now, this is a typical concurrency problem. This is a typical concurrency problem. To resolve this problem, we need to compute the total balance in such a way that it does not interfere with the other transactions, right. Now, how many of you have studied databases? Good. So, a reasonably large number of people. So, you have studied concurrency control, yes or no? Locking algorithms and things like that. Now, the problem here is that our database is we are talking about distributed systems, right. So, concurrency control on one database, multiple processes running concurrently and working on one database, can be tackled by local lock managers. Now, when it is distributed, then how do we actually synchronize between these different agents which are sitting, the controllers which are sitting on the different sites. So, for these reasons we will need to study that how can we work with global state recording algorithms, how can we manage the notion of time and so on. Now, when we talk about synchronization of time between different processes, we should not confuse this with the clock synchronization problem. The clock synchronization problem is another problem which is there. So, where you have this thing that what data is being transmitted by this signal? 0 1 0 1, yes. Now, that is correct provided that this is the clock, okay. If this is the clock, then this is 0 1 0 1. However, if this is the clock, then the data is actually 0 1 1 1 0 0 0 1, right. So, when you are transmitting data across the network from one node to the other, if you just transmit the signal, then you do not know what the data is unless you know what is the clock. Now, if the clock of the sender and the clock of the receiver are not synchronized, then you will read a wrong data, right. Now, that is the clock synchronization problem, where you want to synchronize the two clocks so that they are able to read, the receiver is able to read the data correctly. Now, that is sometimes done by transmitting the clock also along with the data signal, right. Now, there what we are trying to do is we are trying to synchronize the two clocks on both sides in real time, right. Now, when we are talking about logical clocks etc., it is not about, nothing to do with this real time clock synchronization. It is the notion that we introduce to be able to order the different events and the temporal relationships between them, right. whether they happen in the same time on the watch is not important. Okay. So let us see what we want to do. First thing that we want to do is ordering of events. So for this we will use Lamports happen before relationship. You will see a lot of Leslie Lamport in this course. So he is one of the authorities in the area of distributed computing and distributed algorithms. So we will see lot of him in this, and I strongly recommend you to look at his homepage. It's a delight to read. He has some excellent articles about how to write technical papers, how to write them in a way that they are accepted, how to write them so that they are not accepted, and it's a delight. So he's one of the wonderful persons to know about. Okay, so Leslie Lamport's happen before relationship is like this. For two events A and B, A happen before B if A and B are events in the same process and A occurred before B. Okay. So in the same process we can always order the events based on what happened after what, right? Or A happened before B if A is a send event of a message M and B is the corresponding receive event at the destination process. Okay. Then we say that A happened before B, because A sent the message, A is the send event, B is the receive event. So A happened before B. Apart from this, we just use the transitivity relation, that if A happened before C and C happened before B, then we say that A happened before B. Okay. So the happen before relationship has only three types of rules. First one is that if they are in the same process and A happened, A was executed and then B was executed, then A happened before B. If A is a send and B is a receive of the same message, then A happened before B. Otherwise, the only other way that A can happen before B is there is some C such that A happened before C and C happened before B, so A happened before B, right. Now we talk about causally related events versus concurrent events. Event A causally affects event B if A happened before B. So that is how we define. Okay. And two distinct events A and B are said to be concurrent, denoted by A and this concurrency operator B, if A did not happen before B and B did not happen before A, right. So if it is the case that A happened before B is not true and B happened before A is not true, then A and B are concurrent, right. Now let us look at this. E11 happened before E12, right. E12 happened before E23. Why? Because it is a send event, this is the receive event. So this happened before this one happened before this happened before this, right. Okay. E12 happened before E13, E13 happened before E14. Okay. Now look at E11 and E21, they are concurrent. There is no happen before, we cannot say that E11 happened before E21, neither can we say that E21 happened before E11. So they are concurrent. E14 and E23 are concurrent. So just let me erase this. Yes, look at E14 and E23. E14 and E23. Now they are concurrent. Why? Because there is no causal event. I mean, it is not that E23 caused E14 or E14 caused E23. So they are concurrent. But if you look at E22, it causally affects E14, because E22 causally happen before E13, E13 happen before E14, right. So, E14 and E22 are not concurrent, E22 happen before E14. Is the notion of this happen before relationship and causal ordering clear? Right. Now, this is how Lamports logical clock works. So, each process I keeps a clock Ci. Okay. Each event A in I is time stamped with CIA, the value of Ci when A occurred, right. So, what does it mean? That each process keeps a clock. Whenever an event occurs in that process, it stamps it with its clock. Okay. And every time it is stamped, Ci is incremented by 1. Okay. In addition, if A is a send of message M from process I to process J, then on receive of M, process J will update its clock as follows. It will say Cj is the maximum of what it was and Cia plus 1. So, if it finds that the message is time stamped with a clock value such that that plus 1 is greater than its own clock, then it will update its clock, right. This is how the clocks are synchronized between the different processes, all right. Now, let us look at this example. When E11 occurs, P1 stamps it with its own clock 1. Okay. These are the values of the clocks at 1. So, these are the values of C1. These are the values of C2. Okay. So, initially C1 is 1, it stamps E11 with 1. Similarly, P2 stamps E21 with C2 equal to 1, right. And whenever an event occurs, the clock value increments. So, the next event is stamped by 2 here, the next event here is also stamped by 2. Now, when this message is sent, then this clock value of 2, this one, is sent along with this message, right. Now, when the message is received here, this one checks what is its value of clock here. Now, the value of clock here is already 3. Why? Because after stamping this it became 2, after stamping this it became 3, right. Now, this one has a value of 2, so 2 plus 1 is also 3. So, the max of these two is 3. So, it gets stamped by 3. Okay. So, it gets stamped by 3. Now, this one was stamped by 2. So, the next event will be stamped by 3, next event will be stamped by 4, next event will be stamped by 5. Now, when we reach here, at that time you see this message is received. What is the timestamp on this message? 2. Okay, the one of this. Now, 2 plus 1 is 3 and the max of 5 and 3 is 5. So, this gets 5 only. So far the messages have not led to anything being different, right. Now, max of 5 and 3, because this is 2, 2 plus 1. Okay. Now, this was stamped with 3, so this will be stamped with 4, because it is the next event here, stamped with 4. Now, this message will be stamped with 4, right. So, this message will be stamped with 4. Okay. Now, look at this process. this was stamped with 5, so next one will be stamped with 6. So this message will be stamped with 6. Now what is this going to do? From here the clock value that it has here at this point of time is 5, right, and the one that it gets from here is 6. So 6 plus 1 is 7, max of 7 and 5 is 7. So the clock jumps from 4 to 7. Okay, but on this side this one only got 4, and from here it's the value of C1 was already 7. So the max of 4 and 7 will be 7. For yeah, 5 and 7 will be 7, right. So this is how Lamports clocks advance. Is that clear? Yes or no? There are some points to note. If A happened before B, then CA will be less than CB. Why? So if A happened before B, then whenever A happened, suppose A happened here, okay, then at that time it was stamped with some CA, right. Now then there can be a sequence of events E1, E2, E3, E4, 5, E6 and then B. If A happened before B, then there has to be a transitive chain of happen before relationships from A to B by the definition of the happen before relationship, right. Now when we are in the same process, this will increment by 1, by at least 1. When it is going here, we are taking the max of the timestamp of this plus 1 and its existing one. So that will also be at least as large as this one plus 1, right. So on every edge of this chain, the clock is in, the timestamp is increasing at least by 1, right. So obviously whatever CB this one gets stamped with, we will always have CA is less than CB, strictly less. Is that clear? Now the second thing that we need to know is that Lamports, this happen before relationship, this defines a partial order. This defines a partial order. It does not define a total order. Why? Because there are events which are concurrent, right. For example, we did see cases where things like E14 and E23, there is no order between them. We cannot say E23 happened before E14, we cannot say E14 happened before E23. So they are not partial order, they are not total order, right. But there is a partial order because there is, for example, E12 happened before E23 and so on. We can make it a total order by arbitrarily ordering concurrent events by process numbers. This is something which we will see in more details. So, let us keep it for the timing, let us not confuse ourselves. We can impose a total order on top of the partial order by augmenting the timestamps with the process IDs, right, but we will deal with that in due course of time. The problem with Lamports clock is that A happen before B implies CA less than CB, but CA less than CB does not imply A happen before B, right. Now, why is that a problem? Now, consider the following situation. I am receiving messages from different nodes. I want to order these messages as per the causal order. So, if some message A happen before some message C, then I want to deliver A first and then C. Deliver to whom? Deliver to my node, the higher layers of the network. Okay, let me reiterate the problem. I am a node. I am receiving messages from several processes residing in other nodes. Okay. So, I got a message A from this process and I got a message B from that process, and maybe that A happened before B because the message A, okay, after that there was some event in that node which caused a message to be sent to that node, and then that node sent me the message B. Are you following? Right? Let's look at this. There is some node, this message A has been sent to me. Okay, from P1. Now, after this was sent, there was a message which was sent from P1 to P2, okay, and after that P2 sent a message B to me. Now, see, the problem is in P3 I have got the messages out of order. Okay. Now, note that there is a happen before relationship between the send of A and the send of B. Send of A happened before send of B, but I got B before A, right. I want to order it, right. Now, you might say that if A happened before B, then the timestamp of B will always be more than the timestamp of A, right. The timestamp of B will always be more than the timestamp of A. So, when I get A and when I get B, I will see that A has a smaller timestamp than B, that is CA is less than CB. So, I will first deliver CA, then deliver CB, right. Now, that is fine and that is correct. The problem is when you receive B, how do you know that there can be a future A which happened before B and is yet to arrive? Because Lamports clock does not give me the reverse. CA less than CB does not imply that A happened before B, right. So, there could be some, when I get B, I know there may be some message which will come with a timestamp less than that of B, may come, may not come also, and there is no point in waiting for that, because even if that has a timestamp less than B, it may not have causally preceded B, because CB greater than CA does not mean that A happened before B, does not mean. So, the point is, when I receive B, should I deliver it or should I wait? If I deliver it and CA and A comes, and in this case actually CA has happened before CB, then I am delivering messages out of order, right. And if I do not deliver B, then I might wait forever, because I do not know whether there is any other message with a smaller timestamp which will come, right. So, I will wait forever, okay. And what is more, that even if I get a message with CA having timestamp less than CB, it does not mean that CA actually happened before B, whether A happened before B, may not be, maybe that incidentally this has a lower timestamp, right. So, this is the problem with Lamports clock. We cannot use it to sequence the messages, because CA less than CB does not imply A happened before B, okay. So, we will look at a variant of this, which is called a vector clock. What does a vector clock do? Each process Pi has a clock Ci, which is a vector of size n. The clock Ci assigns a vector Cia to any event A at Pi. Now, instead of keeping a single clock variable like we did in Lamports thing, we are maintaining a vector. This vector is the local estimate of the clock values of the other processes, including my process. Okay. So, if there are n processes, I will keep a vector of n dimensions, where Ci will be my estimate of the clock value of I, of the process I. Okay. Now, if you understand that, you will see the update rules immediately follow, that whenever there is an event at process I will update Ci I will increment Cii by 1, because there is a local event which has happened at process I. So, the clock of process I should get incremented, so that ith dimension of this vector will be incremented, right. But this is not communicated. So, the Cj I in the process j is not affected by this. This is a local updation of my own dimension in my own vector clock, right. N is the number of processes. Okay. If A is a send of message m from I to j with vector timestamp Tm, then on receipt of m, Cjk is maximum of Cjk and Tmk for all k. Now, look what is happening here. When we send message, the message carries the entire vector that I has. So, when the process Pi is sending the message m, it will have the vector timestamp Tm, What is the vector timestamp Tm? It will be timestamped with the right, and on receipt of that vector Tmk T of Tm, every dimension of Cj will be updated by taking the maximum of whatever it already knows and whatever it has come to know through Tm. Okay. Suppose the clock here was 1, 5, 2, right, and this message, this is Pi, this is P1 let us say, and let us say it reaches P2, and the clock value here for P2 was 0, okay, let us say 1 and 7. So, when this message is received, the message will carry the timestamp, and I will update this clock here to the max dimension wise max of the 2, right. So, I will update it to 1, 5, 7, right, okay. For the local clock, it will again increment it by 1, because every local event will increment the local clock by 1. This is different. So, we will increment the local clock by 1. So, P2's dimension, namely 5, this will become 6. In the next event here, this will become, in the next event here, this will become, if these are internal events, this will become 187. So, only this dimension will change. So, Pi only changes the ith dimension of its own vector clock, and when it receives messages, it updates all the dimensions.
So when P2 receives the message, it will become 157.
It will no, that increment will not happen. It will not increment the other dimensions. See, this is an event. First of all, before this was 1, 4, sorry, 0, 5, 2. Then it incremented this, send it, and with the timestamp here. When this is received, it will first take the max of this. So, max of this and this is 1. No, that not that plus 1. This is 0 plus 0 and 1, okay. Between these two, 7. So, you get 157. Now, this receive event will increment it by 1, local 1 by 1. So, you will get 167. Clear? That is how the updation takes place. Now, let us first understand the partial order between timestamps. Just 5 more minutes. Partial order between timestamps. Two timestamps Ta and Tb are equal if they are equal in all the dimensions. They are equal in all dimensions. Two timestamps are not equal if they differ in some dimension. Okay. Ta is less than equal to Tb if for all I Tai is less than equal to Tbi, right. It is not less or equal if there exists some I where Ta is greater than Tb. Less than is if Ta is less than equal to Tb and Ta is not equal to Tb, right. What is not less than? If it is not the case that Ta is less than equal to Tb, and if this the not of this is Ta not less than Tb. What I want you to understand is that these are all distinct things, less or equal, not less or equal, less than, not less than. Okay. All right. So, it is possible that two timestamps are such that neither is this less than that, nor is neither Ta is less than Tb, nor Tb is less than Ta, and nor are they equal, right. For scalars it is either less or greater or equal. For vectors it may not be the case that it is less, less means less in all dimensions, greater means greater in all dimensions, equals means equal in all dimensions. What about the case where it is greater in some dimensions and less in some other dimensions? Those two are what we call non-dominated, they are not dominating each other, right. They are the ones which are concurrent. Okay. So, Ta concurrent with Tb if it is Ta is not less than equal to Tb and Tb is not less than Ta. Okay. So, equality, if they have the same timestamp, we will show that then it is the same event, then Ta and Tb are the same event. Yeah. Otherwise, Ta and Tb are concurrent events, right. Not equal, Ta not equal to Tb. So, this less than equal to this means that in every dimension Ta is less than or equal to Tb, okay, and they are not equal in all the dimensions. If they were equal in all the dimensions, if there was, so it means that in at least one of these dimensions this will be a strict less than, okay, that is what it means. Alright. So, we will see in the next class how we can use vector timestamps to arrive at an algorithm for causal ordering of messages.